Okay, I think we're up and running.
Okay, welcome everybody to our weather discussion. If you've not been to this before, we do this every Friday. We're going to start at 12:15 because Professor Petty's in here until 11:50. From 12:15 to about 1:15. It's an informal discussion of the current weather and a forecast. That means it's not a lecture. That means also that I don't want to have to do it every single week. So I'm hoping that there'll be, if something particularly interesting gets your attention and you'd like to talk about it, you are more than free to take over and do it. That's perfectly okay. But more importantly than that, that's just a sidelight to share the burden. But more importantly, there's no need to raise your hand or anything. Let's be respectful, but there's no reason to raise your hand or be overly formal about how we interact during this discussion. Okay, and also, as another means to encourage participation by others, if there is no participation by others, it will be completely biased towards my interests every single week. And that may excite you, but it may not. So you have to, be aware of that possibility as well. Okay. So I think that's enough of the introduction, except to say that we sure do miss the secretary. It'd be nice if he were here. And Professor Tripoli will be back, I'm sure, after his 75-day hiatus expires sometime in mid to late October. So he'll be back. Of course, by then, tropical cyclone season will be over, but that doesn't bother him. He'll have plenty. And I guess one more announcement. Next week, Lance Bosak is staying an extra day to be involved in our weather discussion on Friday. So you don't want to miss that, okay? You just don't want to miss it. The reason we have one here, I think, is because it's modeled after what they've done in Albany for a very long time. So you just don't want to miss that. And I don't know how we'll organize it between the two of us, but it'll probably be mostly Lance or maybe a tag team. It'll be fun no matter what. I'm looking forward to that. So let's start by looking at this. Pete alerted me to this, the Rayleigh corrected visible satellite image over the last probably 6 or so hours. And partly you can see the Terminator coming across the screen, so the early part of it is early in the morning. Look at, first of all, fog in the valleys of Pennsylvania and in New York State. Those were not clouds, I'm sure. They're valley fog. Really cool. And that evaporates away, replaced by some probably fair weather cumulus. But more interestingly, perhaps, is the smoke plume. Look at it. If you saw last night's sunset, if you happen to be sitting outside, around 7 o'clock last night, it was one of those orangey skies. Just really beautiful. That's a function of all of this burning biomass in the western United States, and it's caught in this southwesterly flow all the way from the desert southwest right up to us, and you can't miss it. And it's gone all the way over to southern Quebec very clearly in the satellite movie. In addition, you can see some smoke going offshore from the Cascades of Washington and a real hot spot here in the Cascades of Oregon. Look at that spot right there. It almost looks like a volcano. And that's the plume all the way down to the San Francisco, off the coast of San Francisco Bay. So it's quite literally a holocaust in the western United States. Everything's burning, and occasionally you see with this gorgeous satellite imagery something like that. That's a huge and intense forest fire over a limited spot of Oregon, and it shows up on this satellite movie. You can even see the smoke getting caught in an anticyclonic flow over the desert southwest and heading straight southward along the Yucatan coast, or the Gulf of Mexico coast. And look at how far south this goes, all the way to the southern part of the Yucatan, or the Bay of Campeche. Is that what it is? I don't know what it is, but what it's called. But and when you take a step back from that perspective, you see this extraordinarily deep trough over the western Gulf of Mexico that comes all the way from central and northern Arizona, New Mexico, down to that coast of Mexico, and then back up into Florida, Alabama, Mississippi, and Georgia. So that's really interesting. We're going to want to see that in the upper level charts. So that's one thing to keep our eye on. Another is this linear band of cloudiness to our north and west that stretches all the way back into Wyoming, Colorado. And that's going to be the feature that changes our current complexion of the weather, which is gorgeous, to something that's quite ugly late in the day Saturday, lasting all the way through Monday. So we want to talk a little bit about what are the factors that are going to lead to that diminishment of fine weather conditions in that period of time. So that's something we'll focus on, one focus. I won't focus on Tropical Storm K, which is off the coast of the Baja of Mexico. in California. It's now spreading clouds and precipitation, we'll see on the radar, into San Diego and heading northward toward Los Angeles. So this is an unusual situation for them, not unprecedented. The media would make you think this is part of some sort of a almost biblical crisis. This is not the first time this has happened, but it doesn't happen that often, and especially not so early in the year. And so, certainly worthy of note, but a couple of other things will take most of the time. But you can see the center of the circulation is just off the north coast of the Baja part of Mexico, and the cloudiness is spread all the way almost up to Catalina Island. So it's all the way up in southern California. A more interesting storm is Hurricane Earl, which interesting for a lot of reasons. First, we'll take a little look at it with a different perspective in just a minute, but it's a pretty decently organized tropical cyclone. It's past Bermuda. There's Bermuda right there. I think even the gale force winds have died down in Bermuda, and they had a period of time with tropical storm force winds there. And Earl is now at about 38 degrees north. The underlying sea surface temperature is still above 26.5 degrees C, which is sort of the threshold for continued, well, I should say, sustenance of a tropical cyclone under the right conditions. But I think it's moved into a region where there's a substantial amount of vertical shear. It's my guess right now, because yesterday in our discussion in 452, 751, we looked at the fact that Earl was forecasted to be currently a Category 4 hurricane, and it was yesterday a Category 2. It has not transferred to that higher category. So something rather dramatic went wrong with a one-day forecast in intensity of Earl. Even though it still presents itself as a pretty decent looking storm, it's nowhere near as intense as yesterday's forecast suggested it would be. So we'll talk a little bit about that. But we'll also talk about Earl's fate as it converts itself into an extratropical cyclone further north over cooler waters. And that's kind of an interesting evolution. Not that I understand it in this particular instance, but I can show you some simple cross-sections that will demonstrate how quickly the whole structure dilapidates. And as I say, without explanation, just instead, perhaps to pique your curiosity, mine too, about how this happened in this particular instance, what I should say, what looks like is about to happen. Okay? So those will be the main things we'll talk about. Earl and this linear frontal feature, which is impacting our weather quite soon. In fact, it is right now. The southwesterly flow that brought the smoke is a function of the circulation around this feature. So that's also current weather, but it will be future weather as well, and we'll see some interesting things are going to happen there. And I'll show you some of that interesting stuff with Vis5D, and then other stuff from other locations. So before we go anywhere else, can we go to the broader satellite movie of this feed? Almost the ones that you disparaged just minutes ago.
Color or black and white? Color.
No, let's try color bit. So this is a little bit bigger picture of where we are, and we can put some of these features in context. But Earl looks pretty nice. Again, there's Bermuda. And so Earl's a pretty intense storm. There is cloudiness to the north, which is kind of tied to something in the extratropics, and that's what Earl will link up with for a period of time in an interesting way. And then it'll migrate its way towards the southeast coast of Newfoundland by Monday, Tuesday, maybe even earlier than that, actually. And it'll be an intense extratropical cyclone, but it won't deepen any further after a certain point. However, when it sheds its tropical characteristics, I think it does reach its lowest sea level pressure as an extratropical storm, but only for a short period of time. Sometimes these transitioning storms become major extratropical events and have huge impact on maritime Canada or further east over the British Isles and Iceland. So that can happen. It won't apparently happen in this case. Okay, maybe that's enough on this satellite picture. So let's take a look at the distribution of precipitation across the country with the U.S. radar composite. So here's the feature that's going to be of some interest for us weather-wise over the next several days. And you can see this is largely a linear feature. It's got elements within it are moving at about the same speed as the collection of them. So that's nicely organized, as it turns out. It's on its intermittent rain in Minneapolis today. It's going to slowly sag to the south and east, and as it does so, of course, it has a greater chance of impacting our weather. And that'll be late Saturday, well, we hope late Saturday night, because Patrick and I are playing tennis tomorrow morning. It's a long-standing grudge match, he played in high school. I haven't played for more than 2 or 3 years, and I started when I was 55. So there's a lot riding on it for Patrick. If he doesn't beat me, that's going to look bad for him. If I lose, that's expected. So, I mean, talk about being in a perfect position. But anyway, and Patrick, I should tell you, Min even offered to get us a court indoors in case it rains Saturday. But I declined because I thought if it gets rained out, then that's just fate, and I'll take the rest. So anyway, so give me 1 more week to get better. So that's, you can see most of the motion here is from the southwest to the northeast. There's very little southeastward movement. And there's good reasons for that we'll talk about here in a little bit. Widespread, not particularly well organized convection on the eastern side of what I mentioned. Must be a deep upper trough because you can see even the flow and the smoke on the western side, and then the cloudiness, which is manifest here as scattered precipitation on the eastern side of that. It occasionally starts to look like something's trying to spin up cyclonically here off the coast of South Carolina, but that's just an illusion, I think. And then the west coast of Florida is pockmarked by some convection and a little bit here over the Panhandle and southern part of Alabama. This curved structure in the reflectivity, in fact, is a function of the organization of Tropical Storm K. And so this is the northern edge of that. And San Diego's right here. It's raining all day in San Diego. I mentioned to my class yesterday, my aunt's lived in San Diego since the late 60s. And she says it's really funny. People flock to the beach. They love the water when it's kind of standing still, but if it's falling from the sky, they're petrified. So San Diegans have a little bit of trouble with that, and it's probably one of those days today. But you can see it's making slow northward progress along the bight of California. So that's the broad perspective over the country right now. Let's go to the upper level charts, Pete, to kind of get a sense of how some of these features might be connected to the structure of the weather system. We'll start at 500 millibars, thanks. Totally blank map today, that's unfortunate. So we'll go to the NAM analysis. It's not really that big a difference. The surface, the observations are the same, it's just the analysis is a little bit different. Smoother out in some ways. Okay, so a couple of major features. There's Earl at 500 millibars. You can see that the warmest air is right at the center of it. We'll see that again in a couple of cross sections from some gridded analyses. But lurking just to the north and west of Earl is this upper trough. It's a weak upper trough, but it's there nonetheless. It's discernible. And that is the feature, I think, that's responsible for the cloudiness that obviously is not part of Hurricane Earl, but is in the satellite picture. So these two things are going to contend with one another, and we'll see that in the forecast. Meanwhile, on the northwest coast of Hudson Bay, there's a deep upper low at 500 millibars, and it's from this feature that this reasonably easy to identify baroclinic zone stretches all the way back down towards Salt Lake City. So that's the cold frontal baroclinic zone at 500 millibars associated with the precipitation that's down here right now in the radar. Okay. Emerging out of this northwesterly flow, which is on the downstream side of this ridge that pokes through British Columbia up toward the archipelago, emerging out of this in the next day or two is going to be, and you can almost see it now, a little bit of a cold spot there. There's going to be an upper trough that really gets itself nicely organized. When that feature becomes entangled with the baroclinic zone to the southeast, it's going to change the orientation of that baroclinic zone. Everything that's linear right now is going to start to ball up at the southern end. And that's going to be when we really have the bad weather setting in here. It'll be nicely illustrated by some forecast data that you can present in Viz 5D. But we'll go to 300 in just a minute, but look at where the jet is. There's really no jet at all to speak of until you get over here to the far North Atlantic, over the Atlantic Ocean, but there's a really wavy maximum flow over the western 2/3 of North America, mostly in Canada. So one of the simple ways to measure whether you're still in the summer or whether you're really feeling the autumn is where's the axis of the jet? And if it's this far north, and we'll see it at 300 millibars reflected nicely here, if it's this far north, you're still in the summer, because that's where the boundary is between cold air to the north and warmer air to the south. So a decent baroclinic zone for this time of year. It's cold as -20 over Lake Winnipeg, and it's as warm as -9 at Green Bay. So you've got about an 11-degree horizontal temperature contrast across the states of Wisconsin, Minnesota, and parts of southern Manitoba. So that's pretty decent. Let's go to 300 millibars, Pete, to just see where the jet polar jet structure is, and we'll also go to 200 in a minute. But here's the ice attack maxima, and you can see it's exactly where you might expect it would be, and then you don't see another one until, rather disconnected, until you get over to the north central Atlantic. So this is 138 knots across northwestern Ontario. That's not a weak jet. And then this northwesterly flow all the way from the northern coast of the Yukon Territory down to the border with Idaho is in the 110 knot range, and then it peaks up about 130 just before you get into the United States. So that's a pretty intense northwesterly flow. And as I say, emerging out of this will be, and you can almost see the indentation in the geopotential height here, right here in Saskatchewan. That's going to be the upper trough that impacts the low-level baroclinicity in such a way as to give us a 2-day rain event. It looks like Sunday and Monday, a little bit further into the future. Okay. Notice the complete absence of strong winds at 300 millibars down here over the southern states. That will be very different in the winter. It'll be strong down there. And here's some semblance of that upper trough structure that we surmised had to exist based on what we saw in the satellite picture. I'm surprised that it doesn't extend further down in the geopotential height field, but this is 9,600 meters. And it's really hard to get the next higher contour to be 9720 at the usual contour interval. You just don't find that in the northern hemisphere in the late fall, late summer, early fall very often, and that's what we're falling victim to. There's one isolated value that would fit. But you can see the flow still does obey a geostrophic relation to that geopotential height. If we increase the contour interval, you can see a little bit deeper trough visually, but you can see it in the winds. Let's go to 850 millibars, Pete, which is very instructive this morning. Here's the cyclone. All up to this point, all I'd said was that there was a pretty deep upper low at 500 millibars over northwestern Hudson Bay. Here's the surface, or near surface manifestation of that. 1185 is pretty good for a geopotential height at 850 millibars. That signifies a pretty decent, intense disturbance. And here you can see in the red lines the isotherms, particularly well organized over Lake Michigan, Lake Superior, across northwestern Wisconsin, south central Minnesota, and into Nebraska. That's the baroclinic zone associated with this cyclone. We saw it a little further to the west at 500 millibars. Its warm edge is a little further east at 850. That's indicative of the fact, of course, that it slopes backward with height. But that's a pretty decent frontal baroclinic zone for early September. And the wind shift across it is 180 degrees. It's southwesterly at Green Bay. It's straight northerly at Aberdeen. So you've got almost 180 degree wind shift across that feature, and that's indicative of a pretty strong front. And the geopotential height trough is obvious all the way from the minimum in sea level pressure all the way down to southern Nebraska. And then it gets a little more diffuse, largely because you can't really accurately depict the geopotential height field at 850 over the high terrain. It's not possible to do that. So you've got a pretty decent structure there that makes sense with everything else we've seen to this point. There's Earl. Earl is a monstrously intense low-level circulation. Compare it to K, which, you know, for its latitude is really low. 1,337 meters is a pretty low geopotential height for that latitude, but it's nowhere near as intense as Earl. And just to the north and almost north-northwest of Earl is a region of enhanced horizontal temperature contrast, coincident with a little bit of a vorticity maximum, quite separate from Earl itself. But as I said, Earl makes its way towards this feature, and for a while, the consequence is an intensification of a now extratropical Earl, but when it moves away from this thing, it kind of dies, and we'll show that in the forecast. That's kind of interesting. Okay, let's go to 200 millibars. I should have done it after 300. This will just illustrate, I think, yeah, there's really no obvious subtropical jet separate from this meandering jet stream that we see over the western part of North America. In fact, in research that we're pursuing right now, it's a very straightforward set of ideas. I think, and Greg Tripoli turned me on to this, that in the winter and in the summertime, the polar jet pretty much disappears. And this thing that looks like it's at polar jet latitudes is really the subtropical jet. Whether or not that's true, we'll figure out when we get done with this analysis that we're involved in right now. But its implications will be fairly impressively important if that's the case. So I think it's going to be, I think he's right about that. And now we're just trying to prove it. So, and then the next question is, when in the fall does the polar jet get reestablished and under what circumstances? Very interesting. That's when storms get more frequent in the mid-latitudes. Okay, let's go to What's next here, Pete?
Either the surface or you got your Vis 5B or your,
Oh, yeah, sir, let's look at the surface map. It's probably a little early to see some of the, on today's weather map, to see any of these record things that are going on around the country. Let's start here in Madison. We have 77 over 60. Can we zoom in on that, or is that already zoomed? Okay, that's great, that'll be easier to see. Thanks, Pete.
yep,
77 over 60, you know, for my money, 60-degree dew point is just when I start to get irritated. If it's in the 50s, I don't complain. If it's over 60, over 70, I'm in a fury. If it's in the 60s, I start to complain, increasingly complaints as the value goes up. So it's the lowest level of complaint for me right now. But I would really, like, you can see where it's precipitating, the dew points behind that cold front have gone down into the 40s and 50s. And that means comfortable sleeping nights and reasonable temperatures waiting for the bus with a tie up. Right now, that's not the case. So I'll be glad when that goes out. But it's at this time of year, you really can't expect consistent dew points in the 50s or lower until really the end of this month. And even then, it might be early. So we've got a whole month to go. But pretty moist air in our vicinity. Some places, particularly high dew points in the region. Dubuque is at 64. Waterloo, surprisingly, is 61. Usually they're higher than anybody else. And then if you go further along the Atlantic coast, you can find dew points 70 degrees at Hatteras, 69. I can't remember the name of the station off the top of my head. New Bern, I think, North Carolina, 68 at Charleston, 71 at Savannah, so it gets to be really miserable. 77 in Miami. I don't know how people can live there. 77 at Key West. No, honestly, I don't. I mean, they're nice people, and it's a great part of the country, but how do they live there? With 150 days a year and dew points over 70. How do you stand it?
It was rough.
See? There's personal testimony right there.
I wasn't outside very much.
And then further west, Salt Lake City is only 74 with a 25 dew point today, but they've had a string of days over 100 degrees, which is nearly, I think it is unprecedented. The number of times they've been over 100 recently is just about unprecedented. So the west has been baking. As I say, it's early in the day for them. It's only about 9:30 a.m. or getting close to 10 a.m. now for them. And so you don't see these really extreme temperatures, but even at 10 a.m. in the valley, 91, 90, 88, and these are not, you know, the traditional stations where you go crazy like Death Valley or Needles, Arizona. But it's raining in the southern part of the state, as you can see, with dew points 70 degrees at San Diego. That never, 69, that never happens at San Diego. So that must be really hot for them to deal with. Wow, 69 dew point in San Diego. So pretty wild. Unusual weather there. And if you go all the way up the coast to Seattle, 62 over 50 with, is there another station within 500 miles that's cloudy? No, just Seattle. So, there you go. That's all you have to say about that. Okay, let's take a look at the Vis 5B peak. We got to go back to the beginning time on that when we get to that. And what I'm going to do is, this is now focusing on forecast, but a forecast of the event that's near us. So here is the sea level pressure every 2 millibars from the GFS, initialized at 6Z midnight last night. So this is a 06Z Friday forecast. It's a 0-hour forecast. So here's the cyclone up on the northwest coast of Hudson Bay. Look at the beautiful pressure trough that comes all the way down through central Lake Superior, then connects to another low that's over the baking desert southwest. Absolutely gorgeous structure there. Depicted in the GFS. If we put theta E on top, I don't have an ability to smooth it, I wish I did, but you can see right in here a really strong gradient of theta E that laps right up into the front edge of the pressure trough. So we were talking about this in class yesterday. Where do you place a cold front or a warm front when you're doing analyses? It's on the warm edge of the baroclinic zone because it's easy, and I did it. I have my first analysis still somewhere at home. I was looking for the strongest temperature gradient, and that's somewhere buried in the cold air. That's not where you put the front. You put it at the front edge. Makes sense, the front edge of the boundary, right? So it's easy to see where it would be right in there. Can we put the vorticity on there, P2QZ? Look at this. Take theta E off. Look at this. If you can find the maximum, and I'm helping you do it, that maximum is right along the pressure trough, and the maximum vortex structure coincides with the warm edge of the frontal zone. And so we didn't talk about why, but we will in the future. in class. But that's a really strong relationship that's inviolate, and you can use it when you're doing analyses. If you realize when you're presenting a paper or something, you want to really make sure you know where the front is, and some heckler in the stands can't say, well, that's just your opinion of the front. No, no, no. It's God's opinion, because that's where the vorticity is and the warm edge of the baroclinic zone. So if you've got a problem, you can go upstairs. You know? So that's a really nice structure here. And notice the perfect coincidence between its position and what we saw in the clouds and in the radar. It's really nice at the initial time. Okay, so let's take the sea level pressure off. And then let's just go through one at a time here, Pete, if we could. We'll stay with the vorticity. I should say, this is at about 800 millibars, so 1.8 or so kilometers. And you're going to see, as we page through these, stepping through, and they're every 6 hours, I think, right?
Yeah, or every 3.
Every 3, okay, from the GFS. So you're going to see the linear nature of that vortex strip remain linear for a long time. So let's go ahead. And slowly sagging to the south and east. Linear, linear, linear. It gets weaker or stronger here and there. Linear, linear. Uh-oh, what's happening now? Let's go a couple more times. Well, some of it is still linear. Just about on our doorstep. Now, keep on going. That still looks linear to me. Uh-oh, that doesn't look linear anymore. This part to the north remains fairly linear. This part starts to ball up. So you've got this long strip of vortex substance on the southern end of it at a certain time in the forecast, which we'll note, and then look at why it starts to ball up into something that's more what we call isotropic. That means that no matter what direction you look from its center, the shape looks the same. That's not true of a linear structure. So this gets more and more isotropic, and the vorticity value goes up. It started in the range of about 12 times 10 to the minus 5. It's only almost twice that by the time we get to midday Sunday. So let's go back a couple of times, Pete. Maybe to right there is good. And then let's put the pressure on. This is a 500 millibar pressure, or approximate pressure at 5.4 kilometers. So here's the upper trough that I'll show you in a minute, emerged out of that northwesterly flow. As it gets close to this linear strip of vorticity, it produces local ascent in one particular region, right downstream of the trough axis, for reasons we'll revisit on Tuesday in class. Once it starts to do that, it stretches the column in a local spot, and the low-level vorticity says, whoa, what's going on here? I'm feeling a tug to get in more and more intense, and it stops being linear, and it starts to ball up in that spot. So let's step through these at the same time. Here's the upper trough, and as it gets right on top of that, that's when it starts to ball up. And this is interactive. It's not like the upper trough comes along and doesn't change its complexion. It gets more intense in response to the vorticity that's getting more intense below it. So look at what happens. We get this really pretty obvious upper level cutoff. And if you have an upper level cutoff in your geopotential height, you're going to have an upper level vorticity maxima. I'm not portraying that here. I'm showing you the lower level vorticity. But the upper level vorticity maxima is also positive right in the center of this. And that's related to the Laplacian of the geopotential height. And if you have a local maximum in a Laplacian feature, you have to have a local minimum in the variable that's got the second derivative operating on it. So a local minimum in the geopotential height gives you a local maximum in the vorticity. And if your geopotential height comes down, it means your thickness is getting smaller. And what does that mean about the temperature of the column? It's got to go down. So the lower the thickness gets, lower the heights get, the colder this air is. And if you sit that air on top of this boundary layer, you're going to have a steep blast rate. And it's going to be convection popping up all day on Saturday, well, Sunday and Monday. That's what it's going to be. Intermittent showery weather associated with the development of this upper level cutoff low. And simultaneously, that upper level circulation has taken advantage of the lingering presence of a thin strip of vorticity at the ground that's just kind of getting pumped up and organized in a better fashion. So the circulation will be intense. There'll be a lot of air converging into that low-level cyclone, and that air is going to be subject to very poor stratification, some gentle forcing aloft. It's going to rain. So there's no way it won't rain here all day, well, mostly all day Sunday and Monday. And it's a really cool evolution where you take, the atmosphere always takes whatever's left around. This is a linear strip of vorticity from the prior cyclone over Hudson Bay. The southern end of it gets interacts with this developing cutoff low, and that really spins up the low-level vorticity and makes the heights lower aloft and makes the whole column cold. There's no way you can't get rain out of that. So let's take the vorticity off, go back a little bit, Pete, and try and see where this upper thing comes from. So we'll step backwards. So this is, now we're at midnight tonight, and you really can't see anything except the broad upper trough well to our west and the baroclinic zone. We can put the vorticity back on just for a second, just to remind you that the linear strip of vorticity, which pretty much indicates the warm edge of that baroclinic zone, has moved a little to the southeast, but it's still to our northwest. But there's no obvious feature in this northwesterly flow. Now let's take that vorticity off, and we'll step forward a click or two. Watch in here. This is the region where we're going to start to see some development, I think, if I remember right. Yeah, right in there, over North Dakota. So a little bit more separation between that pressure line and the one to the south and the further one to the south. That's the beginnings of the development of this upper trough. So let's keep going. Here it comes. Right there, it really seems to emerge out of nowhere. And I think we get back to, it was 18Z on Sunday, a couple more clicks. That's when we have this really intense upper level development just to our south and west, sitting on top of that baroclinic zone. So it seems like it comes from very meager, very hard to detect initial conditions, but these forecast models, of course, are excellent now. We will talk in 452 and 751 about how this can happen. What is the process? What's the physical process or set of physical processes that drive that development? So this is an innocuous looking little thing. It's going to give us a crummy weekend, second half of it. But this is the way these weather systems work. They're intricate, but they're really beautiful because they follow rules and you can discern what the rules are. It's pretty fun to be able to do that. Ian?
So if I may pursue that, how do you marry the perspective that you need to lower the thickness to drop into your potential heights? So that's happening because of ascent and adiabatic cooling in the column, or differential advection?
You would have to do an analysis to determine that. My guess would be it's just you have, for reasons that we'll describe in class, for those in 452, 751 a little bit later, to the east of the upper trough, in any state that it exists, this is well developed, but even in the earlier stage when it wasn't, that's where you're going to be forcing ascent. And the ascending air is, of course, going to cool by expansion, and that's going to help you to lower your heights. But generally speaking, the cyclogenesis, that is the generation of more and more intense vorticity, will also be associated with, can't really happen in the absence of column stretching, which implicitly means the air has to be rising through the column, and you get the same cooling.
So how can I marry that to the perspective that I also need to drag the tropopause down?
Oh, well, there's a couplet of vertical motion. The ascending air is here, the descending air is here. And your tropopause structure is going to be brought southward, not southward, downward on the western side of this development. And it won't be moved very much at all, maybe pushed up a little bit on the eastern side of it. So it's the couplet of vertical motion that helps you to marry those two together. And they're phased in such a way that the subsidence which drags the tropopause downward contributes to the next moment's development of intense vertical motion to the east. So they related that one.
Though, where we're dragging the tropopause down from descent, we're also warming that area adiabatically. How do I marry that? I'm trying to decrease the thickness to lower the potential heights, and I'm trying to drag the tropopause down from descent.
Well, the way the tropopause comes down is in terms of the PV, potential vorticity, which just moves along sloping isotopes. So if you're following a parcel there that has a potential vorticity value of 2 PVU, let's say, it's going to slide down whatever isotrope happens to be there. Let's say it's 298. It's going to slide all the way down the 298 isotrope. So its potential temperature won't change. The location of that parcel will change in the vertical. And that will drag along with it the location of the boundary of the high PV. So you're not really changing its potential temperature. It stays at 298. So you're not warming it adiabatically, you're just moving it somewhere else on that adiabatic surface. See what I mean? Okay. So that's all I wanted to say about this thing. But it's a pretty neat example of a really wimpy development. And one more thing, Pete. Let's put the sea level pressure on all by itself at this time. Where's the sea level pressure limit? These are every 2 millibars. So this is 1,016 And there's a little bit of a minimum maybe over Chicago, but it's not even below standard sea level pressure, which is 1,012. Click back a couple of times, you might see a little more structure at earlier times. Or maybe it's later times. We'll go forward a little bit. So that's where we just were. Look at this. That's the low pressure zone, 1,014 millibars. That's going to give us 2 straight days of rain. So it's a really innocuous surface manifestation, but a really, high impact weather event coming up from this development. And finally gets to 1,012. And then a little bit lower than 1,012 for a moment. But it's not a cyclone at the surface to speak of at all, that it's going to be a major weather event. And a really interesting.
We could put the tropopause on there if you wanted to.
Oh yeah, let's put the PV. And let's use the 2 PV value. This 5D is so awesome, we can do these things. Okay, so then tilt it up so we can kind of see where we are. So this is these are like stalactites hanging down from the tropopause. So this is a surface of constant value of potential vorticity, 2 PV units. And then when you tilt it back to the top UP, this shading just indicates it's the Viz5D's attempt to give you a sense of the topography of that surface from that plan view. That's all that's doing.
You can color that by temperature or theta.
Yeah, do it by theta. And then you can tighten that up a little bit and move it around and get that to work. Yeah, and then you got to move the middle value a little bit toward the warmer colors. There you go. And then if we can bring the map to the top, then you can see where we are. Yeah, just roll away to the top. So, and this is at the time when we're getting our cyclone to develop. So blue in this case indicates a low tropopause, the potential temperature is colder at that point in the tropopause, and then red is where it's really high. And here's that intermediate trough that's kind of been organizing the precipitation over Florida today, even though it's 2 days downstream, it hardly moves. But this, go back a couple times, Pete. So you can see where this thing emerges from flow well to the west. Our baroclinic zone is on the front edge of this, and then an upper trough comes along, manifested in this PV that kind of gets the whole thing developed. Go forward, you'll see it kind of almost cut off, even in the PV, but not quite in the PV. It's getting close. That's maybe cut off, and that's Sunday, 11 o'clock in the morning or so. And there's the reservoir of low tropopause is way to the north, and it's got this one little breakoff feature right over us. And that's kind of what we've been describing. So another time when we get another such development, maybe I'll take this perspective entirely and start from the beginning and talk about this perspective on the development as opposed to the one we just did. Okay, thanks, Pete. Look at that. That is a stalagmite. Awesome. Speaking of, let's go to Pivotal, and we'll look a little bit at Earl.
Did you have that up already?
I did, yeah.
Tropical tidbits.
Oh, tropical tidbits, that's what I want, yeah. And we need a different region. We need the North Atlantic region. And that you can do here. North Atlantic, where is it? This one? Yes, thanks. Okay, so this is, oh, you know what? Let's go to the 6Z run, because for some reason, tropical doesn't give you a 0-hour forecast. So let's go back to the 6-hour forecast. That'll be valid. I think you just, I don't know how you go back.
What do you want?
Yeah, I want to go to, to this time, to 12Z.
12Z,
Yeah, that's what I want. Okay, so this is Earl, 965. Clearly not an extratropical cyclone. There's no baroclinic structure associated with this thing at all, except that there is a warm core to it. You can't quite see it maybe from your distance, but the red lines are 1,000 to 500 thickness, and the thickness maximum is right in the middle of the storm. And then here's that little thing to the north and west that we noticed in the 500 millibar temperatures themselves, a little bit of baroclinicity, well separated from Earl. Now, if you do control and you slide your mouse along there, you can create a cross section. So let's get one from about Massachusetts Bay down to about here. Perfect. Right through the middle. Perfect. And then let's go to the PV and then submit. It takes a little while. I'm not sure why. Maybe a lot of people are looking at it today.
They're probably generating on the fly. It's running.
Yeah, they do that.
Cross-section isn't made ahead of time.
It used to be fascinating. But this is, now here we get a reminder of where we put our cross-section from about the Boston area through the center of Earl and equidistance to the south and east. And here's the PV. Where it's blue, the PV is very low, and where it's red and orange, it's very high. And then the dashed lines and solid lines are isotachs of the speed of the wind into and out of the page. So this is into the page, is it? Yeah, and the solid is out of the page. So the structure Earl as a unadorned tropical cyclone, even though it's no longer, it might be only a category 1 or 2, it's a column of PV. It's like a cigar that sticks from the ground all the way up to the tropopause. In fact, the analysis doesn't even go above 200 millibars in the PV. And then a bit of a shadow of something that is totally upper tropospheric, well to the north and west. That'll be off the coast of Massachusetts, maybe. And then the green lines are potential temperature isotropes every 5 degrees. And look what happens in the center of the tropical storm. When you go across at any individual level, the air is warmest, the potential temperature is highest in the middle of Earl, and then colder to the east and colder to the west, or vice versa. And in fact, the warm anomaly is more intense at upper levels than it is near the ground, which is really cool. I don't know if that's always true in all tropical cyclones, but it's true in Earl, and that's been true for a couple of days. Okay, so what I want to show you about Earl is, we'll go back to the surface maps in a minute.
This is kind of interesting. I'm just looking at this, the ground, because we're in pressure coordinates, the ground actually looks like it goes up.
Yes, it does. It does. In reflection of the lowest pressure being there, yeah. At earlier times, or at later times, you see it go up even more. But in a minute, not yet. In a minute, we'll go back to this broad surface map with a larger area and just watch what happens to Earl, clicking through several times. And every once in a while, we'll stop and we'll take another cross-section based upon what the structure appears to be like at the time we're seeing it on the horizontal map. And we'll do it exactly like this. But this is the unadorned or unadulterated tropical cyclone structure that you get when you have Earl, quite separate from anything that might be going on in the extratropics to the north and west at upper level elevations. Okay? Really nice example of what the PV structure of a mature tropical cyclone looks like. Okay, let's go, just click ahead a couple times. We're going to get closer to this feature there, and then suddenly, look at this now. We'll stop here, perfect time. Here's the 1,500 thickness. You can see there's a baroclinic zone on the northwest side of Earl now that wasn't there before. And there's still a warm core that kind of has an extension to the south and east. But I'd really like to see, I thought to myself today, I'd really like to see a cross-section right through that baroclinic zone. Here's the thickness trough, which indicates maybe the close proximity of an upper level feature. But let's do a cross-section like that from Nova Scotia down to about here, maybe, Pete, right through the middle. A little bit more up this way. Yeah, perfect. So we're about perpendicular with the thickness lines. Let's first look at the potential vorticity. And this is, I think we're now 12 hours further ahead than we were. So it's going to be whatever changes we see here occurred, actually, it's 24 hours. Whatever changes we see have occurred in 24 hours in the forecast. So the column of the cigar-shaped PV feature still seems to be there for Earl, but it doesn't go quite up to 200 millibars anymore. It's kind of got cut off at the top. The warm anomaly, indicated by the theta lines, especially in the upper troposphere, are still quite obvious. They're less obvious down near the surface. In fact, I see a little bit of a warm anomaly just to the far southwestern side of that PV column, down near the ground. That indicates perhaps that the structure at low levels is falling apart first. And then look at this. This thing to the northwest is much more robust than we saw just a day before. Now we're in a different place, but here's the upper level thickness trough, and that is a pretty good indication of the presence of an upper level trough at 500 millibars. And that's what we're seeing in this feature right here. And look at how the isotropes look in this case. They bow downwards towards the surface to indicate a really strong horizontal temperature contrast through this upper frontal type structure that's associated with the upper trough. So these things are much closer together. The question is, will they interact in a way that enhances their combined circulations, or will they interact in a way that destroys them? Okay. And that would be manifest, the destruction would be manifest in a weakening of the sea level pressure, and a construction would be even more intensification. Okay, so that's how it looks 24 hours after the initial time. And before we click forward, we can get out of this though, Pete. Before we click forward, I'll draw your attention also to the fact that, I should have showed you this. This is more intense precipitation on that western side of the storm. And I could have shown you, I should have, in fact, we'll do it in the next one. You can opt to look at frontogenesis in the same cross-section. And it's very intense on the western side of the storm. And that's what's producing the circulation now an asymmetric circulation that's driving intense precipitation on the western side of the storm. So though it looks more, as if you're out to sea here, you don't want to be there. And you might not believe that what's happening is actually going to lead to a de-intensification of the storm, because it's raining like crazy suddenly, and the winds are strong, and the circulation around this nascent warm frontal structure is very intense. But it's not going to last very long. So let's go ahead a couple more times. And right about here, it's only 12 hours further into the future, we seem to have shed that baroclinic zone on the western side. Go one more time. Even more obviously, it's gone. So let's now take a cross-section right through there. Perfect. It's right through the center this time. We'll do the potential vorticity again. It's only 18 hours ahead of where we were just the last time. Wait till you see this. I hope it's the same as what I saw today. I think it is. What? The cigar shape is gone. We're only at the light values of PV, like 3 potential vorticity units. We had been residing in the 8 to 9 values. Whatever this thing is in the upper troposphere has kind of gotten skinnier and it's not quite as impressive. That might be a function of the cross-section angle, but I don't think so, because the thickness field does not reflect the presence of any organized upper trough structure anymore. So the upper level feature has disintegrated, and consequently the lower tropospheric to mid-tropospheric feature has also kind of gone away. And look at how disjointed the warm anomaly is. Right here around 600 or so millibars, there's a coincidence between the highest PV and a dip in the isotropes, which means the air is warmer than it should be right there. That's a warm core. But over here, the warm core is on the southeastern periphery of the PV tower, and down here, it's well off the PV tower. So this whole structure has gotten discombobulated in terms of the warm anomaly, and that probably means that it's kind of been sheared apart a little bit by the approach of this upper trough.
So why, did the upper front collapse in that 18 hours, because you're not getting any of that tropopause folding hours in the...
It does look like it has. I hadn't really been attentive to that till I just saw this picture and then you asked the question. It looks like it has. If we go back to the broad view, Pete, without clicking forward, notice how now, boy, it's really hard to find. I mean, the upper trough in the field is back down here probably, because that's where the thickness lines have that curve. And up in this region, maybe we're just cutting in the wrong place, but there's not much structure there anymore. And yet, this storm still presents itself as a real threat for southeastern Newfoundland. I mean, they're going to get heavy rain, extraordinary winds. Look at the pressure gradient, even though tropical draws them every 2 millibars for dramatic effect. But nonetheless, that's an intense horizontal pressure gradient. It's going to be windy. Gale force easy, maybe tropical storm force in northern maritime Canada. And, but yet, this is an extratropical storm by this time. So a very impressive, short-lived fate for its extratropical successor. But now we can click forward and see what happens to it. It still stays intense in the 960s. That's 967, or yeah, 968. Brushes right up against the coast, and then it's going to linger here for a while, and maybe I think it gets up to about 980 or something by the time it leaves the maritime provinces. But it's sitting still, and that's sort of indicative of the fact that it's divorced from any sort of shear flow, any sort of westerly flow. This thing is just out there. It's been orphaned by everything, by the extratropical dynamics and by the tropical dynamics, because the ASC interaction can't occur anymore at this latitude. The ocean's too cold. So it just kind of spins down due to friction quite slowly. 972, keep going, Pete. 976, I mean, these are still impressively deep cyclones. 981 by about midday Tuesday, it's 983. So we'll still see this on the satellite picture on Tuesday when we're talking about it during the weather watch, or weather discussion. But that's going to be about the end of it in terms of a really intense cyclone. So that's what I have for today. So a couple of interesting things going on around the continental U.S. and adjacent waters, and probably there'll be more next week. Don't miss next week. If we get more tropical cyclones, that'll be fun, because Bozart's an expert in that, but he's also an expert in mid-latitude cyclones. And so it doesn't matter what happens, he'll still be expert on next Friday. So that's going to be really cool. So thanks for your attention, and have a good weekend, and I'll see you all next week. Thank you, Pete, for driving.
Probably research.
And Michael, if you're watching, no meteorogram.
Although you did focus entirely on tropical.
I did. That was my compromise.